Campaign community is invited to come to Convocation. And we put it on the local Snow College television, and we also make a DVD of this to put on our file as well. I have a few announcements before we introduce today. Also next week for Convocation, our own visiting Fulbright scholar from Egypt, from Cairo, Egypt, Dr. Nagwa. I have a cell phone here, and if you recall, it's not good to have your cell phones go off in the middle of Convocation. So be sure you turn your cell phones off, like I just did. And I will turn the time over to Professor of Geology at Snow College, Renee Fotz, who will introduce. She's not the guest speaker, she's going to introduce the guest.
I asked if I could introduce Dr. Titus today, so I'll make it quick so you can hear us talk. So 17 years ago or so, I went on sabbatical for a year, and we hired a replacement to teach here, and it was Dr. Titus. And we were really hoping at the time that we could have 2 geologists, one of them be a paleontologist, but that wasn't in the cards. So bad for us, but good for Alan. Alan went on to become the paleontologist for the Grand Staircase National Monument. And he has, we've maintained a relationship with him, and our students have done some neat things with Alan. So I just want to give you a little background for Alan. Alan has been passionate about paleontology since he was a little kid, so those of you that are passionate, don't give up your passion, he'll tell you more. So he received a bachelor's degree in geology from the University of Nevada, Las Vegas, and then went on for a master's degree at the University of Arkansas, and a PhD from Washington State University. Alan actually studied animals called cephalopods, which are shelled guys related to octopi, and that was his specialty. And so he wasn't a dinosaur guy to begin with, but he's a dinosaur guy now. So Alan works as the paleontologist for the monument, as we mentioned, and since coming there about 13 years ago, I've been at the monument for 13 years. The monument, for those of you that don't know, is a really new monument. And when he came there had been 2 species of dinosaurs that were named. And since he has arrived there, they've found 20 new species. So he's done amazing things with, he and the scientists that work with him with the dinosaurs down there. So Alan also, outside of paleontology, which he loves, and it's infectious, is a rock star, just thought you should know that. He has his own rock group called Mesozoic, and he is the lead guitar and vocal, and he and his wife are, and maybe even sometimes son, he does a guest star, okay. So he told me they have a concert on November 2nd in Kanab, so you're all invited to hear Mesozoic play in Kanab if you're down that way. So please welcome Dr. Alan Titus to Snow College.
Thanks so much, Renee. It really is a pleasure to come back and talk. Of course, when I was here earlier teaching, I didn't talk to groups quite this large. But when I get the invitation to come down and do these, I just jump all over them because it's such a great audience. You're all great people, and it's a great place. And in a sense, it's also coming back and connecting a little bit with my roots in my career, and it's nostalgic. So today I want to talk about a particular group of dinosaurs that's one of the poster children, actually, for the end of the age of dinosaurs, the ceratopsids. They have the distinction, some superlatives associated with them that no other group of animals can claim. One in particular is that they evolved the largest heads of any terrestrial animal. So they are essentially the dinosaur equivalent of a rhinoceros, both ecologically and in appearance. Yet they got much more ornate than any rhinoceros we know of in the mammal world. But they grew these enormous, elaborately ornate heads to the tune of 11 feet long. So this is a terrestrial animal with an 11-foot long head at the acme of their evolution. And today I want to, because they're so iconic for the late Cretaceous, basically the end of the age of dinosaurs, they almost have come to symbolize the decline and ultimate extinction of this group, because one of the last dinosaurs to live on planet Earth was Triceratops, which is very famous. Probably all of you have heard of Triceratops, one of the last groups or last species in this lineage of horned dinosaurs. But we've made some amazing finds of horned dinosaurs right here in Utah, all of them new to science, and they're sort of rewriting our understanding of the group, and as our opinion or our view of the group changes, our opinion of the overall dinosaur world is starting to change as well, as far as the ecology of their world, and how these animals interacted with each other, and how predators and prey interacted and how they evolved. These things are changing as we document these new forms from Utah right here. So I'm going to cross my fingers and hope this works here. You never know until you click the button. There we go. Okay, so I want to give you a little background in time first, and then I want to give you an overview of the evolution of the group, where they come from, so that you can see the paradoxes that happen within the group's development as far as their evolution here in North America versus their ancestral home in Asia. And then I want to wind up with the finds that we made in Utah and also the implications of those finds. So we're talking about the Mesozoic for those of you who are non-geology types. And the Mesozoic, meaning middle period of life, is that period that dates between about 250 and about 66 million years ago. It entirely encompasses the evolution and extinction of the non-avian dinosaurs, things that aren't birds. And we're going to be focusing more specifically on the late Cretaceous part of the Mesozoic, which dates between about 144 and 66 million years ago, right? So the Cretaceous is the last of the three major divisions of the Mesozoic. This is the place and time where this group of animal evolves, the ceratopsids. Before I talk about the animals themselves, though, I want to set a little bit of context up for global geography. We'll get to the climate later, and that's an important, very important part of the story, actually. But in terms of global geography, we're looking at a very different world than we see today. In one sense, there are some similarities in that the continents are all, the basic continents we know of today have all started to isolate and form. You know, prior to this, we had this one gigantic landmass called Pangaea, right? Which was very different from today. But by the late Cretaceous, the individual continents were discernible. You know, Africa, there's the Indian subcontinent down there in the South Atlantic, kind of heading up towards Asia. Got Australia, still mildly attached, or marginally attached to Antarctica, South America, and North America. You can recognize the basic shapes. Now, the overall details of coastlines and mountain ranges are radically different. And in particular, I want to point out that at this time, North America was dissected into parts by shallow epicontinental seaways. These are fully marine bodies of water full of sharks and whale-like marine reptiles and everything else. And they are barriers to migration for terrestrial animals. And the ceratopsids actually evolve in Asia and migrate over to North America about 120 million years ago via a land bridge over the Alaskan Straits, over Beringia, you know, the Bering Strait. And they come down and they flourish in the western part of North America on that thin little strip of land we call Laramidia, from Laramie, Wyoming, and the Laramide orogeny. So this is sort of the crucible of evolution for these animals in North America. They never made it over here because of this seaway. So they're really, in terms of North America, they're confined to the western little island or strip of land, isthmus-like strip of land we call Laramidia. And they never made it into South America either. There was no land bridge they could get across. And there may have actually been climate barriers to their migration down there as well. Okay. So, this group, the ceratopsians, which literally means horn face. These horn-faced dinosaurs. Where do they come from? What did their ancestors look like? And ultimately, where did they go? And what were they like just before they went extinct? What are the trends in their evolution? Well, looking down at their origins, if you look at this, this is a tree, an evolutionary tree, or a cladogram. The origins of the ceratopsians are in a small, talking small dog size, like 3 or 4 foot long, bipedal herbivore. Kind of a non-specialized little bipedal dinosaur that's herbivorous. And they develop, this group of non-specialized bipedal dinosaurs, develop a ridge of bone that sort of thickens and reinforces the back of their heads along the squamosal parietal crest. So the back of their skull, back here, they thicken the back of their skull. And at that point, the evolution of this group goes in 2 directions. One of the thickened skull group goes off and becomes something called pachycephalosaurs. Now these are thick-headed, bone-headed dinosaurs that are frequently portrayed as butting heads with each other. They sometimes had crowns of spikes around these thickened skull domes. But they're one group that evolved out of this thickened margin group of non-specialized herbivores. The other one went towards the ceratopsids. Collectively, the pachys and the ceratopsids are called the marginocephalia. Marginocephalia means they've got a rim around the back of their head. That's all it means. This one group of marginocephalians that ends up becoming ceratopsids evolves a highly specialized bone in their upper jaw, at the front of their mouth. It inserts itself in between the 2 beak-like structures called a premaxilla in their skull. Basically, right up here up front. I'll show you a picture in a second. So they insert a 3rd bone into this complex at the front of their mouths that's not seen anywhere else in the animal kingdom. They're the only vertebrates that evolved this 3rd bone in between the 2 premaxilla. It's thought to have evolved to support a very strong beak-like structure that was used for slicing tough vegetation. Come on. Uh-oh. There we go. Okay. So the very first group of these ceratopsid-like dinosaurs, we call them Neoceratopsians. They don't really look like Triceratops, do they? I mean, they're still showing a lot of this sort of non-specialized bipedal dinosaur characteristics. They're still bipedal. They may have been occasionally quadrupedal. They go down all 4s to graze, but certainly most of the time when they're moving around, they're on two feet, and they're not developing the big frills yet. They don't have the big shields projecting out, and they don't have any horns over their eyes yet, and they're still really small. I mean, this animal is about the size of a cattle dog, something like that. Not quite as big as a collie. And they're growing these really thickened, elaborate beaks, and this rostral bone then inserts itself right in here. This is the rostral, the unique bone that these animals all have. These animals are widespread, the fossils of these animals are widespread all over East Asia. And they're called psittacosaurs. And the reason they're called psittacosaurs is because psitta is a Latin name for parrot. So they're literally parrot lizards, parrot dinosaurs. Because of the beaks they're growing, they look like big parrots. Their fossils are found throughout Mongolia and China. They're really common. We haven't found any of them here. So this particular group of primitive ceratopsids never made it to North America. We get spectacular specimens. This guy was literally caught, dead in his tracks, and you can still see the stomach stones that he ingested to help him grind up his last meal, buried right there in the rib cage. We've also found some of these preserved in a place called Liaoning with soft tissue. This is a strange way. I have to... I'm doing that. It's not doing anything either. Strangeness. Okay. There's a side view of a Psittacosaur skull. And you can see this is that rostral bone right here. That unique bone that only this group has. And then some other rather non-specialized kind of dinosaur-looking features. They have sort of thin, leaf-shaped teeth for stripping vegetation, but not really effectively grinding it. They can strip with these fragile teeth, but they're not chewing like we would with molars. They're letting all that work be done down in the gut, the stones. Uh-oh. Are you kidding me? Why don't you I'll remind me later. Now I gotta start the show again. Calm under pressure. Okay. Renee, I'm really going to need that. You wouldn't believe the morning we've had. I had a skull, a big skull to bring in and kind of model all these animals' features for you, and it got broken this morning. $6,000. Anyways, so here's the Psittacosaur, kind of non-specialized looking skull. It hasn't really done much in the way of growing anything out the back. It's just got that one rim or margin of bone. It hasn't started to develop an extensive frill yet. And when these animals do, for whatever reason, when they start to grow that frill out the back, we make a major division anatomically, and I'll get to that in a minute. Okay, so here's one of these spectacular Psittacosaur dinosaurs preserved with soft tissue, like gut contents, skin impressions, and, more remarkably, these feather-like quills that were growing out of the tail. So this led some scientists to speculate that feathers or feather-like structures were actually universal in the dinosaur world, and not just found in the theropod line that, leading to the velociraptors and ultimately birds, that the other main group of dinosaurs called ornithischians actually possess feathers as well. These are probably more like horny quills, like a porcupine spine, but something analogous to a feather. There's an artist's reconstruction of one of these general little early ceratopsids, neoceratopsid Psittacosaurs in Asia. And we've got plenty of evidence of parental behavior and social interaction with these animals. Here's basically a group of hatchlings. They're out of the nest. They weren't buried in the nest, but they're out of the nest, but they're still associating with each other as a group, and they were buried alive by a volcanic ash fall. So they're social. Leading one artist to paint this painting of a mom Psittacosaur with her brood that she's sort of watching over, inferring parental care. And we even have some interesting relationships between early mammals and these Psittacosaurs in this fossil demonstrated. We've got this badger-sized carnivore mammal, an early mammal. It's actually a pretty primitive thing called Rapenomamus that was eating Psittacosaurs, and the remains of chewed-up baby Psittacosaurs were found in its stomach. So Psittacosaurs were mammal food, which is sort of the inverse of the way we usually think about the age of dinosaurs. We usually think of mammals being dinosaur snacks, not the other way around. But in this case, mammals were eating dinosaurs. Okay, so moving on from the psittacosaurs then, as I said, when they start to actually really exaggerate that ridge of bone out the back of their skull and grow this enormous frill, we make a division in the classification, and we call everything above that dividing line. You know, things without and things with. Everything above that's a Neoceratopsid. So, and the most primitive Neoceratopsid, the animal that's psittacosaur-like but starting to grow a frill, is Archaeoceratops, also known from Asia. There's Archaeoceratops' skull. And what they're doing is they're lengthening two major bones in the back of the skull. One of them is called the parietal, right here. That's being drawn out, and the other one is the squamosal. Okay, so these two bones are lengthening and growing rearwards out of the skull. Why? I don't know. There's a lot of speculation that these structures evolved as mate selection, mate competition, species recognition signaling devices, and that they did not have any defensive role to defend their vulnerable necks from predators or anything like that. In fact, they would be a liability later on, and I'll get to that. So there's the most primitive frilled animal that we have, Archaeoceratops. And you can see this is a really interesting case history in evolution where we can almost see every little step along the way to the evolution of these mammoth beasts later on that have the largest heads ever to walk on dry land. Okay, now as the frill gets larger, the head gets larger, and their forward mass is increasing. So the front parts of these animals are getting very heavy. And so what happens to their posture? They have to go down on four legs to accommodate that weight in the head. And so the next big division in these animals is the introduction of obligate quadrupedality. So they're actually now obligate quadrupeds. They're on 4 feet all the time. They're no longer on 2 feet, right? So they go from being bipedal to quadrupedal as the head gets bigger. And the very first group of animals that represents that next step in evolution is the Leptoceratopsids, which are found extensively in North America and not so in Asia, which is interesting. So this must be about when this group of animals made it to North America. They made it to North America at this stage of evolution. And in fact, the next step is as far as they ever got in Asia. So they become quadrupeds, and we have the Leptoceratopsids, right? So there's a typical Leptoceratopsid based on a specimen from Montana. This is Leptoceratops. And you see how massive the head's getting now in proportion to the rest of the body? So they're really growing the size of their head, and they're expanding that shelf of bone. There's an artist's reconstruction of a live Leptoceratopsid. Now they don't put those quills on the tail, but they could have easily had those kinds of structures as well. Now what's next? Well, they just keep basically growing bigger and growing the frill. And the next step then up from Leptoceratopsidae would be the Protoceratopsidae, and these have an elaborate, large frill with big windows inside of it. So these Protoceratopsids are actually sort of the acme or pinnacle of the group's evolution in their point of origin in Asia. That's as complex and as large as they get in Asia. And these animals now become 5 feet long. They're getting 4 to 5 feet long. That's as big as they get. So let's look at Protoceratopsids. See how big that frill is? You know, it's now almost twice the length of the skull. This is still a relatively small animal. Protoceratopsids are very abundant in Mongolia and China, and have one of the most famous dinosaur finds in the history of dinosaur paleontology. Involves a Protoceratopsid here, literally locked in mortal combat with a velociraptor. And the Protoceratopsid, the skull of the Protoceratopsid, this picture is actually upside down, but it's clamped down on the shin of the velociraptor. He actually bit and broke the shin of the velociraptor, and they both tumbled down to the base of a dune and got buried. So this is a remarkable find. So these protoceratopsids, like I said, at the end of the line for the group in Asia, similar animals were in North America, but for some reason, and this is a total contradiction in what you would expect, they go crazy on this narrow little strip of land called Laramidia over here in North America. Over in Asia, where they got all this room and all this ecospace and all these niches they can fill evolutionarily, they basically stagnate at the protoceratopsid level. But in North America, on this tiny little like island subcontinent, they go crazy and they develop a diversity that staggers the imagination. And that's counterintuitive. You would expect the bigger animals to evolve on the bigger landmass. Not so with these guys. So what do? They keep getting bigger with the frill, and they keep getting bigger in size overall, and then they start to add ornament. They start to add horns and hooks and spikes and hatchet blades and all this bizarre headgear to their heads. They just go punk. So there is the most primitive ceratopsoid. It's an animal that's not quite a true pinnacle of the group in North America, but it's getting close. It's called Zuniceratops. It's found in rocks about 92 million years old in New Mexico, and it's got prominent brow horns and a frill that's not much more advanced over Protoceratops. But it's starting to lengthen the face, right? And it still has these primitive sort of weak, single-leafed shaped teeth for stripping vegetation. So it's an interesting mix of characters where it's starting to look like a Triceratops, right? It's got the horns growing out of its eyes. So there's a reconstruction of Zuni. And from this point, the next major innovation in the group is the evolution of a massive slicing dental apparatus. So they're obviously changing their feeding strategy as they get bigger. They're probably dealing with a lot more nutrition poor but tough fibrous vegetation, maybe conifer needles and cycad trunks and things, strips, leaves. And so they're having to process much tougher, thicker vegetation. And so they get rid of the single tooth strategy, and they start stacking their teeth in the same tooth socket. So they have 2 or 3 teeth all lined up in the same tooth socket that basically merge into one continuous sort of mega tooth in their jaws. And these then are oriented oblique to each other and act like a giant pair of scissors. And it's a very interesting evolution or innovation in tooth function. There's one other group of dinosaurs that did this. They're called the hadrosaurs. And obviously both these groups were dealing with the same issues with their diet. So that innovation, more than any other, marks the evolution or the appearance of the true ceratopsids or the true triceratops-like animals. So they have the stacked teeth evolved for slicing as a giant set of scissors. Okay, so that's what they're talking about, the shearing dental battery, right? A battery of multiple teeth, all glued together into their jaw, both upper and lower. Okay, and then they grow the nasal horn, the last little addition to their ornament. The most primitive and oldest named true ceratopsid is an animal called Diabloceratops eateni. It was named for Dr. Jeff Eaton of Weber State, who teaches at Weber State, teaches geology. Actually, he might have retired this year. And this was found in Grand Staircase. It dates to about 81.5 million years old, and it's the oldest true representative of this family. And you can see it has the Zuniceratops-like eye horns, No horn over the nose yet. Well, actually, there's a bump that we're going to count as a horn. There's a little bump starting to grow. It's got an elaborate frill and 2 giant spikes sticking out of the top. There's an artist's reconstruction of Zuni. And now I'm going to talk about details within this pinnacle or crown group of ceratopsids, these horned dinosaurs, just because it's important for my later discussion about the diversity of the animals. So we've evolved the dental battery and nasal horns, and after that point, they basically go in 2 directions, in which I'll sum up really briefly: short frills, right? Short frills and short faces, short noses. So short frill, short face, long frill, long face, drawn out face. So the short frill, short face guys are the centrosaurs, the centrosaurines. The name comes from a guy called Centrosaurus, found in Canada originally. And then the long frill, long faced guys are the chasmosaurines, which is derived from a guy called Chasmosaurus, also found in Canada initially. So you can see long, shallow snouts, elongated rostral, which is, remember that unique bone they put into their front of their mouth. And then the centrosaurs, deep snouts, short deep snouts, and then spikes coming out of the top of the frill. We get all sorts of varieties within these 2 main groups. This is the second oldest centrosaur found in Canada. This is called Albertoceratops, and let's just go back quickly to Diablo. So notice the 2 spikes out of the top, 2 eye horns. What's happening here? They're shortening the spikes on the top, right? Turning those into more of a hook. And they're also shortening the length of the eye horns. They're starting to grow a bump. The bump out of the nose is really prominent. It's actually turning into something. Next step in that animal's evolution is here, Centrosaurus. So those 2 big spikes out of the top are now reduced to forward-pointing hooks. They're growing accessory hooks of about the same length. And they've lost the eye horns altogether, and they're growing a big spike out of the nose. So that's derived from a Diabloceratops-like animal. This is Styracosaurus, the next step in these animals' evolution. You see they're adding really long spikes now to the frill. The face is basically the same as the previous animal. And then this group's lineage culminates in something called Pachyrhinosaurus, which loses the big spike on the nose. It gets reduced down to like this gigantic scab structure. And those guys are found all the way up into Alaska. Now, I said that the ceratopsid evolution stagnated in Asia at the protoceratopsid level, and that's true until near the very end of the Cretaceous, when that Bering land bridge briefly reconnected. And guess what? North American centrosaurs were able to slip over into Asia. And so near the very end of the Cretaceous, just before everything breaks loose and these guys go extinct, there's an invasion of North American ceratopsids into Eurasia, and they just take over. So this is an animal called Sinoceratops, and it's clearly related to Centrosaurus and Styracosaurus. I mean, look at the hooks and the nose spike and everything else. It's obviously a North American animal. There's nothing like it leading up to its appearance in Asia. It has no possible ancestor in Asia. So interestingly enough, when the 2 land masses connected, Laramidia wins as far as the interchange. The tyrannosaurs that evolved in Laramidia, like T-Rex, go over to Asia and kick butt. The ceratopsids that evolved in that tiny little island continent of Laramidia go over to Asia and just take over. And some of our hadrosaurs do the same thing. It's really counterintuitive to what you would expect. Traditional models of biogeography says the bigger land mass usually wins. And in this case, they lost heavily. Sinoceratops. Okay, so now talking about the chasmosaurs, the sort of longer face, longer frills. first thing that develops is not so much the face, but the frill really starts to lengthen. This is Chasmosaurus belli from Canada. This is Chasmosaurus russellii. And this is Pentaceratops sternbergi. This is the owner of the largest head ever found on any terrestrial animal. It's an 11-foot head. It's on exhibit at the Sam Noble Museum of Natural History in Norman, Oklahoma. Amazing animals, just staggering to the imagination to have these gigantic, almost elephant-sized animals with 11-foot heads. And, I mean, guess how long could that horn be, say if you doubled its length? Because that's just the bony horn core. You know, if you add a sheath of keratin, like a nail, growing out of that horn core, how long is that horn going to be? It's just going to be awesome. So there's an artist's reconstruction of Penta, which is sort of the culmination of the Chasmosaur line. And of course, there's Triceratops, which is a Chasmosaur by virtue of its lengthened face and prominent eye horns. But what's the trend now? Well, they're starting to reduce that frill again, right? And there's some recent controversy about whether this animal here is the same as the one on the right with the holes in the frill. The one on the right is called Torosaurus, and the one on the left is Triceratops. And there's been some discussion as to whether Torosaurus is actually just a really big Triceratops, and that most of the Triceratops skulls we're finding are sort of adolescents. So there's Triceratops, the last ceratopsid to ever walk on planet Earth. And there's Torosaurus, which would have been its contemporary down south, presumably. Descendant of Pentaceratops. All right, so now you've had the brief tour of the ceratopsid evolution. You've seen what magnificent animals they are. You can see how North America basically kicked butt during the land interchange because these animals were so awesome. And we're going to talk now about our working grand staircase and the implications it's had on the ecology of these animals and our view of the Cretaceous world. So this is grand staircase. We're basically focusing on the middle part of grand staircase inside the red lines there called the Kaparowitz Basin, which is underlain by Cretaceous age rocks, shown in gray. And it was recognized, 30 years ago by some guys studying early mammals that the Kaparowitz Plateau really was a unique place. I mean, these guys wrote that we've never seen a continuous fossiliferous outcrop of rock like this anywhere else in North America. I mean, if you want to understand all of the change that's going on through the end of the age of dinosaurs, this may be one of the best places in the world to do it, at least in a terrestrial sense, looking at terrestrial ecology. But when I started there in 2000, May of 2000, we only had two kind of scrappy dinosaur skulls, or actually one of them didn't even have a skull, that we could identify to genus or species, which means not much. And so I was a little concerned that we weren't going to find anything. It's like here with all this hype when the monument was created about all the dinosaurs that were out there. I'm like, God, I sure hope we find something. We did. We exceeded all of our collective expectations. Just a quick overview of the rocks for any of the geology types that might have shown up. The stack of rocks by itself is about 8,000, no, sorry, I'm exaggerating. It's about 6,000 vertical feet thick. So it's over the depth of the Grand Canyon. And yet records only about 30 million years of Earth history. So when you figure that all out, you know, when you say, oh my gosh, it's over 6,000 vertical feet thick, and yet it records only 30 million years of Earth history, that adds up to a very continuous story with not many pages torn out, right? So it's really a great place to look at the evolution of terrestrial ecosystems by virtue of where it was located in the ancient geography. So there's a stack of rocks, all have names: Cedar Mountain, Dakota, Tropic, Straight Cliffs, Wawee, and Caparates. So the Caparates is the top formation. So there's the big stack. And I'm focusing on this Caparates formation at the top, and I put this in here so you can see the age of it. So the Caparates dates to between about 76.5, 74 million years ago. And that's great because a lot of the rocks up in Canada and Montana that we're finding these same animals in date to exactly the same time period. There's what the Caparates actually looks like out in outcrop when you're out in the field. This is a view from Highway 12 on your way to Escalon from Bryce, looking north towards Powell Point, which is it's about 10,300 foot top of the plateau with the white. Caparates itself is 865 meters, or about 2,700 vertical feet thick in section. So it's an enormous thickness of rock. And it records only about 2.5 million years of time. So that's an incredibly detailed record of terrestrial ecology. And it's dripping with fossils. There are very few places you go and walk in the Caparates Badlands and not immediately start finding dinosaur bone and chunks of turtle shell and fish scales and alligator scutes and teeth and stuff like that, just laying everywhere. This is another outcrop in a more remote area. We actually end up having to fly a lot of this stuff in, our camps in with helicopters and the specimens out with helicopters. So there's really no roads out in a lot of these basins we work in. Extremely rugged terrain, difficult to hike in, difficult to work in, and it's probably the main reason that we're just now getting to this area. I mean, 100 years ago, nobody wanted to deal with this. It was easier to go to Alberta. Okay, so let's put ourselves in a little bit of context then. Where was the Caparates deposited? Well, it was down on sort of southern part of Laramidia, well within the coastal plain geographic setting, with the seaway now retreating a little east out of Utah. And so by Caparates' time, the sea had actually gone out of Utah. It was over in Colorado. And there's Granite Staircase. And based on all the plant fossils we find, the vegetation was lush, tropical, full-on tropical. Think jungle, think vine-smothered trees and palms and cycads and ferns, tree ferns, things like that. Huge lakes covered with water lilies and water lily-like plants. 40-foot alligators lurking in these lakes and rivers. About 1.8 to 2 meters of rain a year. Well, that's like 6 feet of rain a year based on the plants and the work that the paleobotanists have done. So here's a fossil palm frond from the Caparates. Really a contrast to what we see there today, right? These high altitude red rock and gray rock canyon deserts. Okay, so the very first horned dinosaur we found, way back in 2001, Mike Getty, who was formerly of the Natural History Museum of Utah, was out poking around in the blues by Highway 12 and found a fairly complete individual of this animal, later to be named Utah Ceratops in 2010. Getty eye, after Mike, the finder. And it's a classic chasmosaur, something we might have actually expected to find. It's got the short nose horn, like the classic Chasmosaurus that we saw from Canada. It's got stubby little eye horns, right, coming out the side. Those aren't broken, they're actually the full length, so just little stubs. And the classic long Chasmosaur frill with a few hooks and blades on top. Animals about 20 to 25 feet long, had a 7-foot long head. There's an artist's reconstruction of Utah. Nasal horn might be a little long, but it's a pretty good example or representation of what these animals would look like. And there's just a quick artist's sketch of Utah in an environment with some of the Parasaurolophus hadrosaurs, these really iconic tube-crested herbivorous dinosaurs that we also find lots of. Okay, now the next find that we made was a bit of a surprise. This was Cosmoceratops richardsoni, named for Scott Richardson, seasonal that I hire every year to go out and help me with inventory and collection of fossils. And he found this in 2006. Notice it's radically different from Utah. First of all, it's got super long eye horns, pointing about the same direction, pointing laterally. It's got 10 spikes coming out of the top of the frill, full-on horns or spikes. It's got one out of each cheek and a big hatchet or blade-like spike out of the nose, for a total of 15 blades or spikes jutting out of the head. That's actually the world record now for ornament on the face of a dinosaur, so it's literally the horniest dinosaur ever found. And there's a reconstruction of Cosmo. That's really one of those dinosaurs that captures the imagination, right? We did not expect an animal like this because nothing like it had really been seen anywhere else in North America. So, kind of proud to have found the most extreme chasmosaur in North America. Similar size to Utah. A 5-foot long head with about a 20 to 23 foot long body, or total length. And there's an artist's reconstruction of Cosmoceratops crashing through the undergrowth, terrifying some little raptors. Cosmo has actually gotten quite famous. You can buy plastic reproductions, anatomically correct ones, and you can get a little more fanciful ones because it was featured as the mayor of the town in the PBS, #1 PBS kids show, Dinosaur Train, by virtue of the host, Dr. Scott Sampson, is actually one of the researchers that named Cosmo. So he talked the Henson Group into featuring this new dinosaur from Grand Staircase on their television show. And now you can buy Mayor Cosmo with extreme interaction. It's just an extreme dinosaur all the way around. And this is hot off the presses. This is late-breaking news. Our crews had an amazing field season this summer, and just this October we found 2 new sites that have yielded a 3rd new chasmosaur from Grand Staircase, which is unprecedented. The diversity of these animals in Grand Staircase is higher than anywhere else in North America by at least a factor of 2, and I'm going to bring that point up later. But we found an animal that's close to a named animal called the Convocations marascalensis from Texas. And its characters are a relatively unornamented long frill, no hooks or spikes at the top, and big eye horns, right? And then just a classic little bump on the nose. So this is a known animal, and this new one we found in Grand Staircase may or may not turn out to be a Convocations, but it's a 3rd coexisting chasmosaur, which is an important point to the whole talk. Okay, so now I'm going to turn my attention to the other group, right? The short-faced, short-frilled group called centrosaurs. And we're going to take a quick tour of their diversity. And I'm going to start it by introducing you to Eric Lunn, who is currently a graduate student at the University of Ohio, studying with Pat O'Connor. Eric Lunn worked for the University of Utah back in 2006, and he found a site. There's Eric actually excavating the site with his map grid. He found a site that yielded our first centrosaur, or short-faced, short-frilled animal. Here's that specimen in the middle of being prepared. And the frill is not quite the length of the face. So the frill is about half the total length of the head. Whereas in the chasmosaurs, the frill is actually about 2/3 of the length of the head. And the nose, so here, what we're looking at here is, I gotta step back here for a second. Yeah, the eye is here. The cheek is down here, and then these big horns coming out of the top of the face over the eyes are right there. So I'm going to give you, there's another shot Oh, that's the nose right here. So this is the beak right there. And we actually found skin impressions with this animal, so there was some soft tissue. These are the scales from off one of the legs. And there's all the pieces sort of individually broken out and keyed, but we got most of this animal's head. There's a reconstruction of the animal's head, which I would have had to have showed you had we not had our little disaster this morning. Really extreme short face. Even for a centrosaur, the nose is really compressed this way and elevated this way. So it's really squashed, really high, big nose. And that led to its name, Nasutoceratops, which means big nose, horn face. So it's considered to have the biggest, sort of shortest, highest nose of any of these dinosaurs. And that's one of the key features that allowed us to distinguish it from anything else that had been named. Plus the unornamented frill and the huge forward sweeping, sort of looping, almost steer or cow-like horns growing out of the brow there. And ironically, you know, it looks like a cow, and since a lot of our current controversial issues center around grazing, it's all only appropriate that this animal actually looks like a cow. There's just a pencil, like stipple reconstruction of Nasuto showing how high and compressed that nasal area is. Artist reconstruction, and then the reconstruction of Nasuto that we had done for a book cover, where I'm going to stop and do a little shameless promotion. We just finished a 624-page volume called At the Top of the Grand Staircase that basically summarizes this and all of the other geology and paleontology work we've done in the region. So I've got a picture of Nasuto on the cover. And his last name is Titus, because he was named for me. Yeah, so this is my baby. And he ended up on the book cover not just because it was my dinosaur. He ended up on the book cover because this animal, more than anything else we found, really symbolizes the uniqueness of the dinosaurs we're finding in southern Utah. There really is nothing like it found up north. I mean, even Cosmo has something that vaguely recollects it called Vegaceratops found in Canada. But Nasuto has no equivalent up north. It's just an extreme variation on centrosaur theme. Okay, I don't even really want to get into this. This is more the technical side of the evolution of these animals. Okay, so what I want to do now is put these finds in Utah then in a context. So, why are all these animals new? Why aren't we finding things that we found already up in Canada and Montana, which isn't all that far away? I mean, it is far, but it's not all that far away, especially when you consider there appeared to be no physical barriers to their migration. Right? It wouldn't be that big of a deal for a centrosaur or a chasmosaur to walk from the Judith River Badlands in Montana down to southern Utah, given what we infer from the ancient geography. These are the 5 major areas we've been finding these age animals. Big Bend, Texas, the Aguja Formation, San Juan Basin, the Kirtland-Fruitland Formation, they're up by Shiprock, GSE&M, Grand Staircase, down in south central Utah. You notice there's no place really between southern Utah and Montana that we're getting any data, and that's a big black hole. If you go out and find me some dinosaurs in there, I'll bet you we can answer a lot of these questions that we posed. Then we have to jump all the way up to northern Montana and the Judith River Badlands before we pick these guys up again. And then up in the Red Deer River Badlands of southern Alberta, some of the most famous finds of this age anywhere in the world. Well, before we start comparing these faunas, these different groups of dinosaurs to each other and making some inferences or conclusions about them, we've got to make sure we're talking about animals that lived at the same time. Otherwise, we're really comparing apples and oranges. So we want to make sure we're comparing apples to apples and that they lived at the same time. When Cosmo was alive, whatever was up in Canada that we're comparing it to was alive at exactly the same time. Well, fortunately for us, we've had some recent work done by Dr. Eric Roberts, now at the University of Queensland in Australia, who dated all of these beds. He went through and he analyzed the ash falls from ancient volcanoes in the Comparawits and came up with hard numbers that we could compare with numbers that we found in the other formations. So we get dates out of the Wawi, we get dates out of the Comparawits, showed by the red stars. We get dates out of the Canadian sequence, right? That's Alberta. And look, we do have one exact overlap between the upper part of the Belly River group, known as the Dinosaur Park Formation, and the Comparawits. These animals we can show conclusively lived at the same time. That's important. When we go over to New Mexico, those animals are slightly younger. And the other formations in Canada also younger. So, but if we talk about animals in the Dinosaur Park and the Comparawits, we can be sure we're comparing apples to apples. This is Centrosaurus. This is the Centrosaur that dominated Canada at 75.5 million years ago. So, it doesn't look anything like Nasuto. I mean, they found bone beds of hundreds of these animals buried together. They're clearly the dominant Centrosaur up in the north. And of course, Nasuto. So let's just go back and forth here. Long nose horn, short frill, hooks. No nose horn, long eye horns, no hooks on the frill. Really extreme variation in the Centrosaurs between the two places. Totally unexpected by us. So somewhere between the two regions, and this pattern more or less expresses itself in every major group of dinosaur that we've documented. It's just easier to show in this group than the others. But somewhere then between Grand Staircase and Montana and Alberta, there's got to be a barrier. Something's precluding, whether it's ecological or physical, something's preventing these animals from interacting. And yet we can show that earlier, back in the 80 million to 85 million year range, they were interacting. There are similarities. So something happened. We'll get to that in a second. So if you look at modern biodiversity in general, there's always exceptions, but in general, the trends tend to peak at the equator, where you get rainforests in the intertropical convergence zone, where there's lots of moisture, and it's hot all year round, lots of lush growth. You get your New Guinean rainforests and your equatorial African rainforests and your rainforests in Brazil and the Amazon, places like that. That's where we see peak diversity in virtually every group on land. So you would expect that if the Cretaceous world were the same, that diversity would keep going up as you went south, right? However, recently there's been research that shows the Mesozoic world was radically different than today. It was much hotter. In fact, 16 degrees centigrade on average hotter in the Cretaceous than it is today. Now, if your average temperatures are, say, 100 plus, and you add 16 degrees to that, centigrade now, I'm sorry, 100 Fahrenheit, and you add another 20 to 25 degrees to that, you may actually be creating lethal conditions for large vertebrates in the tropical realm. And so these researchers, looking at the lack of large animals down in the equatorial realms in the Mesozoic, have said, oh my gosh, it may have been so hot for a lot of the Mesozoic, especially in the post-Triassic extinction world, that there just wasn't anything alive down there. These were literally dead zones in our planet, where we resembled Venus more than Earth. So there would have been these sort of extreme vegetational biomes, plants that were adapted to extreme heat and extremes in precipitation. And it wasn't until you got up into the higher latitudes that things cooled down enough that animals, large tetrapods, large reptiles and amphibians and things like that could actually adapt and cope, and mammals even. So, and there's another thing too, that the atmosphere at this time was radically different. There was a lot more carbon dioxide and a lot less oxygen. So there are some people that have proposed the oceans were actually lethal in the tropics, not just the land, because of these extreme elevated temperatures that we're seeing of this runaway greenhouse type climate. So perhaps instead of looking and thinking about biodiversity peaking at the equator, we should be looking for these peaks at higher latitudes where the conditions are livable. And it's my inference, my presumption, that we may actually be looking at a biodiversity peak up here in Utah, which may explain something. May explain why we find 5 coexisting horned dinosaurs in the Comparoids and only 2 up north. And I have to mention, I did a study on all the other groups, turtles, lizards, snakes, mammals, and all of that. And I've been able to show that in each case, every one of those groups peaks in southern Utah. Starts lower diversity up north, it peaks in Utah, and it actually starts to taper off again as you go down into Texas. So we, by some strange twist of fate, may actually be sitting on peak diversity for the Cretaceous ecosystem in North America down in southern Utah, which means the sky's the limit. We may find many more species of dinosaurs, The animals we're finding in Utah are largely limited to the southern portion of Laramidia. They weren't making it up north, maybe because of climatic or ecological barriers, presumably not physical ones. So we may be looking at sort of a hot tropic to cooler tropic climate difference, creating a barrier between these sort of tropical animals and sort of subtropical or or cool tropical. That the ceratopsid evolution is much more complicated than we thought, that we're looking at 2 to 3 times the diversity of these animals on this tiny little strip of land at any given time, which is staggering. I mean, think of, it would be the same as having like 10 or 15 species of rhinos coexisting in Panama and Guatemala. It's just hard to imagine how these animals can be so diverse in such a limited landmass. And the final take-home, or the final point I want to make, is that these animals, this crucible of evolution in Laramidia, actually created animals that for some reason, when they finally faced competition with animals that had been evolving and happy in Eurasia, the larger landmass for millions of years, just took over. They just trampled these things in their wake, and basically the very end of the age of dinosaurs in Asia looks like Laramidia, because the Laramidia dinosaurs won that struggle, that ecological struggle. So, of course, it all came to an end, 65.5 million, and leaving us with lots of questions to ponder. And I think that as we grapple with these concepts of much greater dinosaur diversity at any given time, and how dinosaur ecology is so fundamentally different, that these animals can evolve in such small land masses and gain such huge sizes, that it will help us maybe understand their extinction a little better. So, thank you very much. I'm sorry I actually went long. I'll be happy to answer any questions anybody might have about this talk, or dinosaurs in general, or about our performance next Wednesday, or next Saturday. Anybody? Yeah. Yes. Yes. Yeah, Very subtle, though. In most cases, dinosaurs don't display the really dramatic differences that we see in a lot of mammals, like especially I think of cervids, deer and things like that, where the male has a big rack and the female doesn't. The differences that we see in male and females, presumably in dinosaurs, are mostly size and exaggeration to a slight degree of some of the ornament. But we've done studies on large populations of these animals from bone beds in Canada. Presumably, we're not finding all 100 females buried together and 100 males. And we found multiples, and there are differences, but they're subtle. And they almost have to be teased out statistically. So we don't see the dramatic differences in boys and girls, but presumably the females would need some adaptation for carrying big clutches of eggs and things like that. So there are pelvic differences too. Yeah?
So, the example you showed of the toy dinosaur, right?
Yeah.
I think of like the Stegosaurus cartoon dinosaurs I grew up with.
Right.
I was visualizing, imagine, the sort of kind of rounder, wider shield or frill on them. And a lot of these skulls we're looking at, one thing I noticed here more than previously is how narrow and sort of elongated and narrow they are. And some of these slides have been in forests and stuff. Some of the slides are on forest, some are on grassland.
Yeah.
I don't know. Do we know why they're sort of oriented more sort of vertically like that? That's in between trees or?
That's a great question. There have been a number of ideas raised about why these frills grew the shapes they did. Because obviously there's some pressure driving the evolution of these extremely large structures that presumably would be a detriment to the animal. Especially with all these hooks. If you're trying to get through undergrowth, that's going to slow you down. Snagging things on brush and all of that. Why did they do that? Well, first of all, our view of the animal's shield shape is largely biased by our familiarity with Triceratops, which was an end member, kind of an extreme end member of the Chasmosaur lineage that was retro-evolving its frill back to a short, stubby, round shape. It actually had an ancestor that had a long frill. And so most of that family actually had these extremely long frills that made up, 2/3 of the total head length. So why did they do that? The most popular, I would say, most widely held explanation for or belief for this is sexual selection, mate competition, species recognition, species signaling devices. So they would be like the crests and plumes on birds or racks on deer. These are all structures that are just about reproducing and communicating with fellow members of the herd. So now you start to see, flashy patterns, color patterns painted on them by artists that are reconstructing these animals now, instead of just this sort of reptilian gray-green color. That may not be the only explanation. They're certainly not defensive. Okay? One widely held belief a ways back was that these were to protect the vital areas of the neck from predators. As you can see, some of them are so thin and so drawn out that they would be so easily broken through by a tyrannosaur with the crushing bite force of tons and tons of pressure. So, and in fact, they were so vascularized that he probably would have bled to death if a tyrannosaur bit in one of those. You can see that the surfaces of those frills are literally covered with massive arterial ways for blood vessels to flow into them. One bite into that and he'd just bleed out. It would be like cutting your femoral artery. So they're not defensive. They're not using those to protect their necks. I have my own personal idea developed recently, and it's based on the pattern that the short-frilled ones dominate up north and the long ones dominate down south. So we've got overwhelming dominance of long frills down south, overwhelming dominance of short frills up north. What if they had a heat function? And they're actually radiators. Then the hotter it gets, the bigger you want that structure to be to dissipate heat more efficiently, right? So that's not a new idea, I didn't make that up, but I started to apply this to the chasmosaurs, looking at the dominance of one group versus another. I just think whoever came up with that idea was on something. I think it may actually have a functional purpose as far as heat goes. Because we see a similar pattern in the crested hadrosaurs. The ones with the really big structures are down south, and the ones with the reduced structures are up north. And they're taking each breath and running it through this elaborate tube system in their head before they actually bring it into their body. And I think that they're doing it more elaborately down south to cool it off before it goes in. Yeah, Paul.
Where do you go to see these things, go to museums and out in the field?
A lot of these animals are on exhibit up at the museum in Salt Lake. So if you go to the Natural History Museum of Utah, up next door to Red Butte Garden, up in Research Park, the skulls of Utah, Cosmo, Nasuto, and Diablo, I think, are all on exhibit there in the main exhibit hall area. And then I think the actual bone, the original bone types are on exhibit behind the glass in collections. And you could also see them working and preparing some of these fossils in the lab. They have a big fishbowl lab that you can watch them work on the fossils in. So, yeah, if you want to know more about this stuff, I encourage you, when you're up in Salt Lake, to just stop by the museum and check it out. We have a lab down in Grand Staircase where we're preparing bones continually. I've got a crew of 13 volunteers that come in every week and help us work on that stuff. So the public's always welcome. If you ever find yourself in Kanab Monday through Friday, 9 to 5-ish, feel free to stop in at the headquarters there and see if I'm in, and I'd be happy to give you a tour and show you the real thing. And then Renee offers a field trip every year where she brings her geology. Which class is that? Yeah. The Geology 101? Yeah, brings her geology kids down to Grand Staircase and we go out and do a dig. So maybe that's some incentive to sign some kids up for geology. If you've ever wanted to dig a dino, see Renee. Yeah. Yes, we have looting, we have theft. It's not systemic and it's not probably to the same degree that's being experienced out on the San Rafael Swell or the the Hanksville, Henry Mountain area or around Moab. I mean, professional looters stealing bones are rampant out there. But because it's in the monument, we do have gun-carrying rangers on patrol and all of that. I think we're able to keep that kind of systematic, commercial looting out of Grand Staircase. We're experiencing more of the casual stuff where a guy will drive his ATV out and spend an afternoon and walk around and pick up stuff. Yeah, we have had a couple of quarries looted where we were in the middle of digging and somebody came in and, while we were away, picked stuff up, worked stuff out of the quarry. But it's a difficult place to work, and even the looters know that. Anybody else? Yeah.
Where do you stand on the Triceratops Torosaurus issue? Do you think they were two separate species?
I do. And that's because we've found lots of Torosaurus down south and no Triceratops. And they've got one or two Torosaurus up north and all these Triceratops. And it would just be an amazing statistical coincidence if, we just happened to miss all the Triceratops down here. Don't you think? Yeah, I mean, they found Torosaurus up on North Horn Mountain, right here by Ephraim, but no Triceratops. Why is that? So, my personal bias is they're two different animals, and that they may be evolutionary continuums of each other, right? Because Triceratops evolved from a long frilled ancestor, and so there's going to be intermediate stages, animals that look like a Triceratops but still possess a long frill. And it would be easy to kind of gloss over the differences and say, oh, well, the faces look the same, it's just the frills, and they're just growing those as they get older. But they may actually may share an ancestor-descendant relationship as well. Does that make sense? Yeah. Yeah?
On the subject of the Torosaur Triceratops debate, what about the possibilities of a salmon-like migration, basically on the northern side of things, would be the breeding grounds, and they would bring them down? That be a possibility?
So is that as an explanation why we don't find one?
Absolutely.
Okay, repeat your question.
Basically, what would the possibilities be that maybe the saying the Torosaurs were Triceratops, when you get the idea up, that it was following more like a salmon migration almost, that the Triceratops were, or the Torosaurs or Triceratops, whichever one it would be breeding up north. The juveniles would stay up there and they would move south. What would the possibilities be of that?
Well, these animals are communal. I mean, they live in herds, and they exhibit parental care. And it's hard to imagine that they would abandon their young and just the adults would make the return trip. I know they grow an enormous amount. We've been able to show that dinosaurs probably achieve 25 to 30% of their adult body size in their first year, which is staggering when you think of an animal that's the size of the elephant. But they're still, they couldn't mature past the Triceratops developmental stage, I would think, by the time they would migrate south. Does that make sense? So I would think somehow. Now, admittedly, we don't have lots of them. There aren't lots of places where you can go and find the right age rocks to dig them up in the south. But in the few places that we have, we just don't find Triceratops. We find everything else. We find T-Rexes, we find Torosaurs, we find a sauropod called Alamosaurus, which we don't find up north. And so I just get the bias that it's a distinct dinosaur assemblage in the south, and that Torosaurus and Triceratops are distinct. I think they have one, basically Jack Horner and Denver Fowler have one specimen that they think is transitional. And that's what their whole argument is based on, is this single specimen. That they think they can see the frill, the fenestrae or the window in the frill starting to open up in. And again, I don't know. My bias is against that. Anybody else? Great, all right, well, thanks.